Imagine a highly precise robot arm, diligently performing its task, when suddenly it appears to freeze or make an unexpected, jerky movement. It seems to have lost its sense of direction, even though all its motors are functioning perfectly. This curious behavior isn't a malfunction in the traditional sense, but rather a fundamental geometric limitation. The core cause of a kinematic singularity in robot arms is a specific geometric alignment of the robot's joints that results in the manipulator losing one or more degrees of freedom. In simple terms, the robot finds itself in a configuration where it cannot move its end effector in certain directions, even if its joints are capable of motion. It's like trying to perfectly align 3 points on a line. Once they are aligned, small movements in one joint might not produce any change in a desired direction at the tool point. This phenomenon is rooted in the mathematical relationship between the robot's joint velocities and the end effector's velocity in Cartesian space, which is described by a powerful tool called the Jacobian matrix. When a robot reaches a singular configuration, this Jacobian matrix becomes rank deficient, meaning its determinant approaches zero. This mathematical condition implies that the matrix can no longer be inverted, which is essential for solving the inverse kinematic problem to determine the necessary joint velocities for a desired end effector motion. Essentially, the robot's internal control system loses its ability to calculate unique joint commands for certain directions, leading to unpredictable or stalled motion. To practically understand and mitigate singularities, roboticists often employ several strategies. One common approach is to implement joint limit avoidance, where the robot's path planning algorithms are designed to steer clear of known singular configurations. Another technique involves using redundancy, adding extra degrees of freedom to the arm so it can navigate around singular points by utilizing different joint combinations for the same end effector pose. Furthermore, trajectory planning can be optimized to smooth out paths, reducing the likelihood of encountering singularities at high speeds, which can otherwise amplify their disruptive effects. A fascinating detail is the distinction between wrist singularities and arm singularities. Wrist singularities, common in six-axis robots, occur when the last 3 wrist joints align, causing the tool to lose its ability to rotate around one axis. Arm singularities, on the other hand, typically happen when the arm fully extends or retracts, making it unable to move perpendicular to its axis. Recognizing these specific types helps engineers design more robust control algorithms and plan more efficient, singularity-free movements. The Jacobian's condition number, a metric derived from the Jacobian matrix, provides a valuable quantitative measure of how close a robot is to a singular configuration. Ultimately, understanding kinematic singularities is not just about identifying a problem, but about recognizing an inherent design characteristic of robotic manipulators. By comprehending the underlying geometric and mathematical principles, and by employing smart planning and control strategies, engineers can ensure robots operate smoothly, predictably, and efficiently, unlocking their full potential for complex tasks without unexpected interruptions.
If you love robotics, like, subscribe, and keep building with us.